Today's class, I wanted to move on from the work we did on numerical solution of partial differential equations to work we're going to do on digital signal processing. Actually, there's some links between the two topics because in the numerical solution of partial differential equations, we made difference equations out of the partial differential equation. And in the digital signal processing, we often make difference equations in processing the data. So I just got a couple of slides of introduction, one about digital signal processing in general, and then another one about digital signal filtering. And then we're going to explore a couple of filters that you've met before. They're filters that you meet in general physics. So they're the filters that correspond to simple RC circuits that make a low pass filter and a high pass filter that let through low or high frequencies. So we'll talk about those. So when we think of a signal, when we imagine a signal, we think of it typically as describing how one variable changes as another variable changes. So think about voltage as a function of time. That's a classic example of a signal carried on that voltage variation as a function of time. So in that case, we would think of the time variable as the independent variable, kind of the domain, and we would think of the voltage variable as the dependent variable, kind of the range. And so that's an example of a signal. An important thing about signals is that signals carry information. So signals communicate information, and that's why we're interested in signals. So classic examples of signals and information are audio signals, they carry information, video signals that carries information. In the context of, say, experiments in different areas of physics or different areas of science, it might be sensors or instruments or detectors that, say, measure light or temperature or pressure that are as signals and carry information, communicate information. So in the natural world, things like voltage and time are continuous variables. In our digital signal processing, our corresponding voltages and times are quantized variables. So when we talk about digital signal processing, say experimental information, then we're imagining that there's some sort of analog to digital converter that has taken sort of nature's analog signals and turned them into digital signals. And when we talk about voltage variation versus time, we imagine that the voltage and the time are now quantized. So the time is now just coming in discrete units, and the voltage has discrete values. So in the case of voltage versus time, we might represent our voltages, say, by 12 bits. We can use 12 bits to represent the values of the voltages. And we might represent time by a certain number of samples per second, maybe 1,024 samples per second. So in that way, both the voltage and the time are quantized in digital signal processing. So digital signal processing itself is really just a sort of combination of mathematics, algorithms, techniques, computing to process or manipulate your digital signals in that digital domain. So the sort of things that we might do are to shape your digital signals, to clean up your digital signals, to filter digital signals, with the idea that by shaping or cleaning or filtering or transforming, we are able to analyze and extract some useful information. We're able to analyze and extract the interesting information. So digital signal processing is basically everywhere. So, within science, we turn our analog signals into digital signals and process them. Within engineering, they turn analog signals into digital signals and processing. Within medicine, things like electrocardiograms or MRIs, we turn the analog signals into digital signals to process them and extract, analyze the information that we're interested in, extract the information we want. So very famous and recent example of digital signal processing is the detection of gravitational waves. So in the gravitational waves experiments, it was in part through very, very sophisticated detectors, but also in part through very, very sophisticated digital signal processing, that the signals of the gravitational waves were extracted from the raw data. Okay. So digital signal filtering is a part of digital signal processing. It's a subsection of digital signal processing. It's used for a couple of main purposes. One is to separate a signal carrying some information from some noise, some background. And another one is to restore a signal to its original form if it's been distorted or warped in some way. So an example of extracting a signal from noise is in an electrocardiogram. The electrical signal that you're interested in is kind of bathed in a background noise. And so you use digital signal processing to extract the signal that you want, say the heart beating from background noise. An example of restoring a signal to its original form is that when you send a signal, communicate a signal from one location to another location, typically you distort that signal in that communication from one location to another location. And so you'll do digital signal processing to restore the signal from its distorted, warped version into its original sort of pure version. So you're familiar with analog filters for signals, and we're about to talk about digital filters for signals. An advantage of digital signals filtering for signals is that you can obtain much higher quality digital filtering than you can with analog filtering. So an example might be you can build, or you can code, or you can construct a digital filter that has the following properties. So you could build it such that it has a gain of 1, so unity, to a part in 1,000 for every frequency up to 1 kilohertz. It would be perfect, almost perfectly equal gain of 1 up to 1 kilohertz. And you could design it to have a gain of very close to 0 within a part of 1,000, a gain of 0 for frequencies above 1 kilohertz. And that transition between the gain of 1 and the gain of 0 can occur in just like 1 hertz. So a part in 1,000 of the frequency, of the cutoff frequency. So that's an extraordinarily high quality filter of a 1 and straight down to a 0 within 1 hertz at 1 kilohertz cutoff frequency. You could never design that with analog circuits. You could never build that with resistors and capacitors and inductors. One of the problems with resistors and capacitors and inductors and analog circuits is the reproducibility, the quality of the resistors, the inductors, capacitors. So in the digital world, everything's very reproducible, and you can build much better quality digital filters than you could build out of analog components for analog filters. So when we talk about a filter, actually whether it's an analog filter or a digital filter, we often talk about describe it in 3 distinct ways. And these 3 distinct ways are equivalent to one another, which means that if you described it in one of these 3 ways, you can always map it into the other 2 ways. And these 3 ways are the impulse response, the step response, and the frequency response. So those are 3 different kind of languages: step response, impulse response, frequency response, for describing a filter. So, you know, this particular filter has a set of impulse, step, and frequency responses. Another filter has a different pattern of impulse, step, and frequency responses. So it's kind of the language that we can use to describe quantitatively a particular filter. When we implement filters in kind of the digital domain, with digital signals, there's 2 basic ways that we implement the filters. In one case, we give it the name of sort of convolving the input. We describe the fact that we're convolving the input to get the output. The other one involves a kind of recursion on the input and output to get the output. So there's these 2 basic classes of digital filtering, one involving a convolving algorithm and one involving a recursive algorithm. So I wanted to say a few words about those. We'll meet both of those over the next couple of classes. Today is really the recursive algorithm, and in the next class we'll meet the convolving algorithm. But they're the 2 basic types. So in the case of the convolving algorithm, and it's described by this little equation down here, the output, so an output sample, an output digital sample, is determined by a sum, a weighted sum of input digital samples. So that's how we calculate each output sample. It's just the weighted sum of the input digital samples. So that's what this equation is saying here. So X is the input and Y is the output. The indices here, n and n minus 1 of X, refer to the particular input samples. So as we look backwards, we see current sample n, the prior sample n minus 1, prior sample before that n minus 2, before that n minus 3, and so on and so forth. And out of those samples, x to the n at the input, x to the n minus 1 at the input, x to the n minus 2 at the input, we're going to calculate the output. That's y to the n, the nth y. And we said we would do that by some sort of weighted sum of the input samples. And these coefficients, b, b0, b1, b2, b3, those are the weightings. And so this is an example of a digital filter that's based on convolving. Convolving the input with some sort of response that's described by the parameters b0, b1, so on, to get the output. And so that's a convolving filter. The other type of filter, I said, involves both calculating the output sample, both from the input samples and also from prior output samples. So it uses both the up to the current input sample And also it uses prior output samples. And so that's described by this second equation here. So if you look at this second equation here, again, the symbols mean the same thing. So xn, xn minus 1, xn minus 2, those are the input samples up to the current sample. Yn is the current output that we're going to calculate. Yn minus 1, Yn minus 2, Yn minus 3 are prior output samples. So they're the history of the output. And so in this recursive digital filtering, not only do we use directly the input, a weighted sum of the input samples, but we also combine it with a weighted sum of the prior output samples. So A0, A1, A2 are the coefficients of the prior output samples. And so that's the second type of filtering. So these two diagrams are basically diagrams showing those two filtering approaches, digital filtering approaches, the convolution approach filtering, and then that recursive technique for filtering. So, and they maybe show it more visually, pictorially than the two equations that I showed you. So if you look at the convolving filter that's upstairs here, here comes the input in on the top left-hand side. So it's the xn's. It's a stream of samples, a sequence of samples with different indices. Here goes the output. It's theyn's, again, a stream of output values, a stream of output samples. The output is calculated from the input by summing up the current sample with some coefficient, the prior sample, so this is like a little delay that takes you to the prior sample with some coefficient, the prior sample before that, so this is another delay, we add in the prior price sample, and so on and so forth. So this is a picture or a sketch or a cartoon of that convolving relationship. This is the corresponding sketch of the recursive filter. So again, over here on the top right, left, is the input. So this is X, the input, which is a string sequence of samples with indices or labels and. Here's the output over here on the right-hand side. Again, a resulting string of samples derived from the input. But you see, in this case, not only do we add up, make a weighted average of the input samples. So the input is passed down here, and we make a weighted average of the input samples with some coefficients, the B's. We also feed back the output, and we make a weighted average of the prior output samples and feed that into the current output sample. And so that's the recursive filter. Okay, so the next few slides, I want to remind you of very simple filters in electrical circuits based on combination of a resistor and a capacitor. You can build a low-pass filter that lets through low frequencies, high-pass filter that lets through high frequencies. There'll be a reminder of how to build those out of resistors and capacitors. Then we're going to write a digital filter, construct a digital filter that represents, in the world of digital signals, a low-pass RC filter, and we're going to look at its properties. And although we won't do it, you'll see how to make a corresponding high-pass RC filter as a digital filter, and you'd be able to examine its properties too. So this little circuit here on the left-hand side made of one resistor and one capacitor is a low, what we call a low-pass filter. So if you were to apply a signal, a voltage signal, say, between the two inputs on the left-hand side, and you were to read out the voltage signal on the right-hand side over here, what you would find with this little circuit is that low frequencies would pass through from the input to the output, so it's a low-pass filter. High frequencies would not pass through from the input to the output. And there would be some sort of cutoff between what we mean by a low frequency, what we mean by a high frequency, which would be which we would call the cutoff frequency. So this is how to design with analog circuits and analog components a simple circuit passing low frequencies and attenuating high frequencies. You can see how it works by just thinking about, say I suddenly apply a voltage, V0, between the input terminals. What do I see on the output terminals? Well, the moment I apply that voltage V0 on the input terminals, this capacitor is still uncharged. It's uncharged, it has no voltage across it. And so I don't see anything at that moment T0 on the output. With time, though, this capacitor starts to charge up. As the current flows through the resistor, the capacitor starts to charge up, and the current flowing through the resistor starts to decrease. And so with time, what you see is a voltage appears across the output, because the output is the voltage across the capacitor. And ultimately, this entire applied voltage gets applied across the output. And so you can see here that it's passing a low frequency. So if we wait a long time after changing the voltage on the input, we'll see that voltage on the output. So it's transmitting with low frequency, that change, but it didn't respond to the very high frequency step of initially applying that voltage on the input. We saw nothing on the output. And so this acts like a low pass filter, a low pass RC filter. The time constant for the frequencies that are passed and the frequencies are attenuated is determined by the product of the resistance and the capacitance. So that's a time, and that sets the scale of what we mean by a low frequency or what we mean by a high frequency. So that's a low pass filter. This would be a high pass filter. So I've now taken the same resistor and capacitor, say, but I've rearranged the circuit a little bit to build this little circuit here. So over here again on the left-hand side is the input to the circuit. So I'm going to apply a voltage to the input of the circuit. And over here on the right-hand side is the output to the circuit. And again, let's imagine that we apply a voltage at some time, T0, we apply a voltage V0 on the input. What do we see on the output? And you can think of the charging up of the capacitor due to this application of this voltage here and due to the current that's going to flow around the circuit through the resistor. So initially, there'll be no voltage across the capacitor because no charge has had any time to flow onto the plates of the capacitor. And so the entire voltage will be across the resistor. And so we'll see this voltage spike on the resistor the moment we apply the voltage at the input. But as the capacitor starts to charge up and the current is flowing through the resistor, then we'll see as the capacitor gets more and more charged up and less current flows through the resistor, we'll see a reduced voltage. across the resistor at the output. And ultimately, when the capacitor is fully charged up, then we'll see no voltage at the output of this circuit. So this is a high pass filter. So in the short term, it let through the step on the input. So we suddenly increased the voltage on the input, and that passed through the filter. So the high frequencies of that step got through. But on the long term, if we wait a long term, we see nothing on the output. The low frequency associated with this step don't get through. So this is a high pass filter. So what I just showed you for the high pass filter and the low pass filter were what we call the step response. That's one way of characterizing the filters. So I applied a voltage step from 0 volts to V0 at the input of the low pass filter, or the input of the high pass filter, and we saw the response at the output of the high pass filter and the low pass filter. And we saw that they were quite different responses. We saw that one let through low frequencies, one let through high frequencies, one attenuated high frequencies, one attenuated low frequencies. Another way of characterizing the filters is, again, the frequency response. So now I just want to show you two equivalent slides for the frequency response. So this is the low pass filter again, this RC circuit. Again, on the right-hand side, left-hand side, I'm imagining applying this time a sinusoidal signal rather than step function. So that's in red. And then here's the output that I get on the output side of the filter. In these two plots, I'm showing you the output relative to the input. So imagine taking the output signal and comparing it to the input signal. That's what I'm showing you here. If the amplitude is 1 of the output, that means all the input got through. If the amplitude is 0, that means none of the input got through. And so for this low pass filter, if we start by looking at this top plot, I got horizontally frequency. So over here, horizontally is low frequency. Upstairs here is high frequency. Here is the cutoff frequency. This is the sort of division between passing frequencies and attenuating frequencies. And here we're seeing the amplitude of the signal with respect to the input that gets out of the filter. So at low frequencies, we see this full input coming to the output. So it's a gain of 1 for this circuit. At high frequencies, we see an increasing attenuation. Only a small fraction of the input gets through to the output. And so this is the filtering, and this is the low pass filter. There's one more plot here which is interesting. It's the same horizontal axis frequency from low frequency to high frequency, but it's a phase. This phase is the difference in phase between the input phase, so it peaks here, and the output phase peaks here. So at low frequencies, there is no phase difference. So actually at low frequencies, you put in a signal, you get out a signal. The sizes of the output signal is the same as the size of the input signal, and the phases of the input and output are the same. So the signal just passes through the low pass filter. As you move towards the cutoff frequency, what you find is two things start to happen. One, you get a slightly smaller output than the input. Second one is that the phase of the output is slightly different from the phase of the input. So they're no longer in perfect phase. And if you pass through the cutoff frequency, you start to see much smaller output than your input. And you also start to see a large phase difference between the output and the input. And actually, the way we define the cutoff frequency is the frequency where the phase difference has become 90 degrees. So whenever the input is a peak, you've got a node on the output. Whenever the input is a node, you've got a peak or a trough on the output. So this is the picture of this RC low pass filter in the frequency domain, and it's equivalent to this picture of this one of the low pass filter in the step function domain. This is the high pass filter. So in the high pass filter, we rearrange the capacitor and the resistor, and I've got a sinusoidal input now on the input. I've got a sinusoidal output on the output here. And for the high pass filter, what you see is at high frequencies, the input signal is simply transmitted to the output. So whatever input amplitude, you get the same output amplitude. The gain is 1. And whatever the phase of the input, you get the same phase for the output. So the phase difference is 0 degrees here. But if you were to lower the frequency, first you start to see that the output amplitude gets a little smaller than the input amplitude. You'd see that the phase is slightly different between the output and the input. As you pass through the cutoff frequency, then you'd start to see a big difference, a much bigger difference between the input and output amplitudes, and a much bigger difference between the input and output phases. And again, the cutoff frequency is defined as the frequency at which there is a 90-degree phase difference, pi by 2 phase difference between the input and the output.